Hi everyone. So yeah, as Lucy said, been involved in a lot of the Popheart modelling work, and just wanted to share some of the recent findings from some of the that work, how we've been modelling sexual risk-taking behaviour and looking at the dynamics of the epidemic in regards to the different groups of sexual risk-taking behaviour under different interventions of universal test and treat. And I just wanted to start by just describing sort of more broadly kind of mathematical modelling and how it's used. So epidemiological modelling is used in sort of two broad ways. It's used in to understanding mechanisms or patterns of transmission, and it's used to make projections of the impact of interventions. We very often see mathematical modelling used in this way, for instance, in policy documents and so on. And there's two broad styles of model. There's what I'll call analytic models, which are quite often called compartmental models, and individual-based models. So analytic models are typically phrased as differential equations. This is the sort of canonical, most straightforward analytic model called the SIR model. And it's three sort of coupled equations that describes the flow of a population between different compartments. So you have S, which is the susceptible individuals, you have I, which are infected individuals, and R, which are removed individuals. So this is a very common model for modelling epidemics. So these are known as compartmental models. It's key to keep in mind that the epidemiological unit typically in these sorts of models is the population or a subpopulation. It doesn't have to be, but it typically is. This is a unified mathematical framework, so we have a common formalism, and there's some fantastic benefits to that, in that these models can then be manipulated using mathematical tools. So you have a whole swathe of mathematical tools. There's a big mathematical toolbox for interrogating mathematical equations. And because we have a model written down in a unified framework, we can look at things like thresholds, theoretical thresholds, upper bounds, long-term behavior, and a whole range of very useful ideas that we couldn't do if we hadn't phrased it in a common framework. These sorts of models can be deterministic or stochastic, so including variability, and they're very commonly used in the earlier sort of foundational literature in epidemiology, epidemiological modelling. So this is a sort of very straightforward type. We can write code for it in quite a small number of lines of code, and we can generate a solution for it. So a solution, by that I mean values of these SI and R that would satisfy the equation in question, given some starting conditions and parameter values of these beta and gamma values. That's a very, very simple model, but you can make it a lot more complex, and you can add additional heterogeneities by including different compartments. So for a much more complex model, HIV models are typically quite complex because you want to take into account a huge range of heterogeneities. So as an example, the model published led by Anne Corrie, that was a sort of precursor to the main Popheart model that I've been working on, was an ODE model, and it included many different compartments that included not just transmission, different compartments of infection status, but also early and acute HIV infection testing, so therefore awareness, different treatment compartments, circumcision, adherence, and viral suppression, and different compartments of disease progression, sex, and groups of sexual risk-taking behaviour. So these sorts of models can be very complex. The other type of model that is commonly used, and these are by no means the only two types of models, they're just two very common types of models, and I'm a little bit biased. They're the two main types of models that I've been most familiar with. So the other type of model is called an individual-based model. These are also known as agent-based models. And the key difference here, I guess, is that the epidemiological unit in this case is an individual. It's not, you're modeling individual level, you're modeling individuals, their characteristics and their behaviors, rather than the population as a whole. So it's very useful for modeling individual level interventions. These sorts of models are typically quite complex and have much larger code bases than analytic models. They're typically stochastic. You could argue that they potentially include greater realism because of these individual level interventions. And they've only really, and on certain scales, they've only been recently possible with computing power. So whereas analytic models have been around, or compartmental models have been around for a long period of time. So a lot of the common models that you hear of are individual-based models or a hybrid that include some individual-based component. So how is sexual risk-taking behavior modeled within different types of models? I was a little bit overwhelmed at this topic. I think it's very large. There's a huge number of ways in which it's taken into account. I think in the most straightforward way, the simplest way in analytic models, the population is split into different compartments, different levels of sexual activity or sexual risk-taking behavior. So if we consider the diagram I showed before, where you have susceptible individuals, infected individuals, and recovered individuals, you could split this population into those with a high level of sexual activity and a low level of sexual activity, and you could have interactions between them. So you could have transmissions from individuals moving from a high level of sexual activity. You could have transmissions between different levels of sexual activity in the population. So for instance, transmission would be characterized in a matrix showing transmissions between individuals in the high sexual risk, sexual activity compartment to others in the high sexual activity compartment, high to low, low to high, and low to low. And this sort of formulation gives rise to the idea of assortativity between different groups. So this is the idea, it's a measure of propensity for individuals to partner with individuals of the same characteristics. So if you have high assortativity, individuals who are both from the high sexual activity class would partner together, and if you had low assortativity, it would be more like random mixing. So other approaches that are taken in different models, it very much depends on the formulation of the model. And individual-based models, particularly because of their complexity, can take sexual risk-taking behavior into account in a huge number of ways, including the rate of partnership formation and dissolution, whether or not concurrent partnerships are taken into account, condom usage, serodifferent partnerships based on HIV status, and partnership types, different regular partnerships, casual partnerships, commercial sex workers, and so on. So I wanted to highlight some of the work that we've been looking at that's related to looking at sexual risk-taking behavior within the model used within the Popheart study, so HPTN 071. So Popheart, for those who are not familiar with it, is a cluster randomized trial in 21 high prevalence communities in Zambia and South Africa. And it took place between 2014 and 2018. It's a very large scale HIV prevention trial. And it was a 3-arm trial with 2 intervention arms, arm A and B, and 1 intervention arm that was one control arm, a standard of care arm, arm C. And in arm A and arm B, there was a combination prevention package that was delivered by community HIV care providers, or known as CHIPs. And these were a man and a woman that would go around. They were allocated 500 households each, and they would go around and offer household testing, HIV counselling, and linkage to care, promotion of condoms, and uptake of ART upon positive HIV test. Within Arm A, ART was offered universally. This was before universal ART has been rolled out in these countries. And in Arm B, it was offered at national guidelines. And in Arm C, it was just standard of care. There were not these community HIV care providers going around, but ART was offered at national guidelines. Beyond the CHIPS intervention, in order to measure the impact of the intervention, population cohort was carried out. So that was followed for 4 rounds, and it was a random sample of 18 to 44-year-old adults, about 2,300 individuals from each of the 21 communities. And it was within that was the primary endpoint of the trial was measured. As part of the trial, an individual-based model of HIV transmission was developed. And this included a huge range of different components, including modeling of demographics, partnership formation and dissolution based on individuals, a measure of risk-taking behaviour and age, and location, so whether an individual was in a particular Popheart community or outside a particular Popheart community. HIV transmission was modelled, disease progression and AIDS death, and there was both a background HIV care cascade and a Popheart intervention that was modelled. And both of these included HIV testing, antiretroviral therapy, and voluntary medical male circumcision. This is an individual-based model, so we could get some very detailed outputs from this model. So we could look at HIV prevalence, incidence, ART coverage, and look at the complete transmission network as well, because we can model that. So we fitted the model to each of the 21 communities, and this is just illustrating from one intervention community some of the data that we fitted to. So shown in the rows are data fitted to women by sex, by age and sex. So this is prevalence data. It first shows prevalence of women, men, then women and men. The different rows, so the shown in brown is the data from the population cohort, or orangey brown is shown in data from the population cohort. Blue is data from the demographic and health surveys from 3 different years of that. And shown in green is data, HIV prevalence data from the final round of the CHIPS intervention. So just putting labels over the top of these. This is from the start of the trial, then 12 months after the start of the trial, 24 months after the start of the trial, and 36 months after the start of the trial, and so on, different time points from different sources of data that the model was fitted to. We also fitted to different 90s, so awareness and proportion on ART, and the proportion virally suppressed. So this is showing age and sex stratified fits for the first 90 on the left-hand side here. So this is from intervention data. So it's showing age and sex stratified proportion awareness of HIV status given HIV positive individuals. So rounds 1, 2, and 3 of the intervention data, 3 rounds of the intervention data for proportion on ART given awareness of HIV status, and we have 24 months after the start of the trial, age and sex stratified viral suppression data. So we can see that the model fits reasonably well to a large range of data. So what we were looking at is how different interventions as modeled, these CHIPS interventions would change the dynamics of HIV in different risk groups within the trial. So how was partnership formation and dissolution taken into account within the model? We only modeled heterosexual partnerships, and there were 2 important processes that we modeled. So age mixing, and the idea that individuals prefer to partner with those of similar age, and risk groups. So this accounted for variability in sexual risk-taking behaviour. And all the data that we used for parameterizing these were from the population cohort data. So that was the random sample of 2,000 participants from each of the 21 communities, and they were 18 to 44 years old. So we modelled 3 groups of sexual activity or sexual risk-taking behaviour. It's a proxy for sexual risk-taking behaviour. And these were found by looking at the extended questionnaires of sexual behaviour from the population cohort, and looking at individuals' age and the number of lifetime partners, and finding a cutoff across this space so that we would maximise differences in prevalence between those three different groups. So we have high-risk individuals where they have a relatively large number of lifetime partners for a given age group, medium risk somewhere in the middle, and low risk where it's a lower number of lifetime partners. Hello, is someone? Okay. And so within the model, we're sort of representing these groups as having very similar behaviours. So, as mentioned, these were based, these 3 different groups of sexual activity were based upon age and lifetime number of partners from extended surveys on sexual behaviour. The 3 different groups differed in the maximum number of concurrent sexual partners that were allowed in the model. So we looked at the number of concurrent sexual partners as reported in these sexual, in the behaviour surveys as output in the trial data. So the low risk group had 1 concurrent partner, medium risk group had 3, and the maximum number of concurrent partners in the high risk group was 10. And the other parameter that was varied for different partners, for different risk groups, was the mean duration of partnerships. So 15 years on average for low risk group, 6 years on average for the medium risk group, and 4 years on average for the high risk group. So we included a measure of risk assortativity, and this was calibrated in the model. So we allowed the inference framework to choose what this should be. And as mentioned before, this is the propensity for individuals to partner with those with similar sexual risk-taking behaviour. So for instance, if we had low assortativity, risk assortativity, on the left-hand side here, I've got a diagram where it's a sort of heat map showing propensity to form partnerships with individuals of a particular risk group. So we have low, medium, and high risk group along the bottom, and low, medium, and high risk group along the y-axis. And the colour is showing the propensity of individuals of those sort of partnerships to form. So there is a diagonal, so there is some propensity for partners to form risk groups with individuals in the same risk group, but it's more evenly spread out. Whereas if we have a higher assortativity, individuals within the same risk group are only partnering with individuals in the same risk group. So we allowed the model to adjust this parameter so that the data would, so that we could best fit the data. So using our calibration framework, I showed you fits before to the observed data, and they were showing 1,000 projections from 1,000 parameter sets from our calibration framework. And if we look at those 1,000 parameter sets and we look at the distribution of HIV incidence and prevalence in those different risk groups through time, we get something that looks like this. So I'm going to show you cross sections of a simulated population of a Zambian intervention community from the very start of the trial, and I'm going to show you 2 measures. On the left is HIV prevalence, and on the right is the size of that risk group as a proportion of the total population. So each of these distributions shows the output from 1,000 different simulations. And we have, in descending order, low, medium, and high risk group going down from top to bottom. So on the left-hand side, we can see we see HIV prevalence, and as you would expect, it's much lower it increases as you increase with risk group. And on the right-hand side, we have the proportion of population subgroup. So in the low risk group, we have about 50% of the population. So in brown is women and in blue is men. So we have in total, about 50% of the population is in the low sexual risk group. In the medium group, we have about 30%, and in the 35%, and in the high risk group, we have about 15%. If we look at the male to female prevalence ratio, we can see that that's decreases as risk group increases, and so does the variation in the prevalence ratio. And if we look at measures across the course of a simulated trial, we can look at measures of both of HIV acquisition, so HIV incidence on the left, and onwards transmission, so the probability that an individual transmits HIV during the trial. This is in a simulated trial. Oops, excuse me. So as we might expect, there's much higher HIV incidence in the high risk group, and the probability of onwards transmission of HIV during the trial is a lot. The differences between men and women, as we saw in the HIV prevalence ratio, decreases for an increasing level of risk, and also the difference between medium and high risk group is not as marked as one might expect. So we do have a much higher incidence in the high risk group, but if we take into account the fact that the medium risk group is a lot larger in absolute size, if we look at the total number of the total number of transmissions over the course of the simulated trial, and we look at, well, what proportion of transmissions were from individuals of one risk group to another risk group, and we split these both according to, on the left-hand side, female to male transmissions, and on the right-hand side, male to female transmissions, we can then look at the proportion of transmissions across those risk groups. And if we take into account the actual size of those risk groups, although the high risk group has a lot higher incidence, we see a lot larger proportion of transmissions from the medium risk group to medium risk group over the course of the simulated trial. We then looked at, well, what's the implication of these, how do these dynamics change for long-term projections? So we looked at a range of different scenarios, and I'm just going to show you two scenarios until 2030. The first was implementation or simulation of the Popheart trial, and then continuation of a CHIPS intervention or a UTT-like intervention until 2030. And that was compared with no intervention, so a counterfactual scenario. So no Popheart trial and then no Popheart intervention to 2030. And these are the three different figures, three different measures. So at the top you have, so along the x-axis is time, so from 2010 to 2030. On the left-hand column panel is the first intervention that I was talking about, so the simulation of the Popheart trial and then continuation of a CHIPS intervention. And on the right-hand side is a counterfactual, so no simulation of the Popheart trial and no CHIPS intervention. On the top row is HIV prevalence, in the middle row is total incident cases, and on the bottom row is the proportion of incident cases in each risk group. And there are three different risk groups shown here. In red is the high risk group, in blue is the medium risk group, and in green is the low risk group. So we can see that HIV prevalence overall is declining. Popheart intervention starts in about 2014. So we can see there is a large reduction in total incident cases in 2014 in scenario one. But what's most interesting is if we look at these projections to 2030, although we have declining incident cases and we have declining prevalence, there's a concentration of new incident cases in the high-risk population compared to a counterfactual scenario. So although HIV epidemic is declining, we're concentrating it into that high-risk population. So in summary, a sustained universal test and treat intervention, such as the CHIPS intervention, predicts a substantial drop in incidence. And the model predicts the continuation of a UTT approach to 2030 predicts that an epidemic will become more concentrated in those with the highest levels of sexual risk-taking behaviour. So just to summarise, there's large heterogeneity in sexual risk-taking behaviour in the population. And this correlates with HIV acquisition risk, meaning that we can, using these within mathematical models, can help us understand patterns of HIV transmission. Improving sort of causal pathways between interventions and behaviour change can allow mathematical modelling to help better predict the impacts of different interventions. And within the Popheart modelling work, we found that implementation of a universal test and treatment intervention to 2030 predicts concentration of HIV epidemic in those with highest levels of sexual risk-taking behaviour. So with that, I'd just like to thank the Popheart modelling team particularly, and Ethan Wilson at Sharp for interesting discussions, and thanks very much.